Okay, greetings. The purpose of this video is to go over some of the things we encountered in our last AP classroom assignment. The name of the assignment was Limits Check 2. The assignment posed some problems for some people, and so we want to kind of address them. I was on the virtual hours with two different groups, and with both those groups, I actually went over the whole assignment. So there were a lot of questions on the assignment. So I want to kind of address them. Now, everything on the assignment was stuff that we have done before. It was over concepts we have covered. But sometimes even when stuff is over concepts we have covered, it still can present problems, and that's okay, because we're just a few weeks into the course. And as we get more and more into this, things will make more and more sense to you. So it's understandable to be fuzzy about a few things now. So I just want to drive some things home. I say all the time, this is a very technical course, and you have to make sure you have a very deep understanding of material and exactly understand what a statement says and what a statement does not say. So what I have here is a statement where it says the limit as x goes to 1 of f of x is -2. And we really need to understand exactly what that statement is saying and what, if any, implications that statement has. So let me tell you what the statement is saying. This statement is saying the limit as x goes to 1 of f of x exists, and it is -2. I think we'll all agree that statement is saying that. So the question is, are there any implications to that statement? Meaning, does this statement tell me anything about continuity at x equals 1? Does it tell me anything about the value of f of 1 or f of 1 existing? So does this statement at all address continuity, the value of the function at the point? Now, something you saw on one of your answer choices, it even talked about f prime of 1. But we haven't gotten to derivatives yet. So, and that may have caused some issues for you because you guys may have seen answer choices over things we haven't covered yet. But I submit to you, when you're doing an AP classroom assignment, if an answer choice is over something we haven't covered, then that's not going to be the answer. So one of them says something like f prime. I'm not going to explain why that's not the answer because we haven't went over derivatives yet, even though some of you are familiar with derivatives from pre-cal, but you don't understand derivatives in terms of its relation to a limit or continuity. So you don't really have to worry about this, you know. And one of them said, is it differentiable, I believe. Again, we haven't talked about differentiability, and which really is really kind of the same thing as this. So again, you may, when you do AP classroom assignments, see answer choices that talk about derivatives and other things we haven't covered yet. They will never be the answer. The answer will be over something that we covered yet, that we have covered. So I apologize if that caused some confusion. So my real question, based on what we have covered, does the existence of a limit tell me anything about continuity or the value of the function at the point? I hope you have an answer to that question. So, and the question, I'm sorry, so the question in the assignment and the question I'm asking is a must question. So if the limit exists, does it have to be continuous at x equals 1? Does f of 1 have to exist? Not saying could it exist, but does it have to exist is really the question I'm asking. So let's take a look. So I have a graph of a function whose limit as x goes to 1 equals -2. And let's see if it has to be continuous or if f of 1 has to exist. All right, so here's my function, and you can see The limit as x goes to 1 is -2. Okay, so you see the graph of this function. Would you mind telling me what's the value of f of 1? Oh, you're right, it's undefined. The limit exists though, correct? So here's a clear example that the limit can exist, and you should be aware of this, but the function not be defined at that point. And if the function is not defined at that point, can it be continuous? Absolutely not. So it has a removable discontinuity right here. So just because the limit exists doesn't mean that the function has to be continuous or that the value at the point has to exist. I mean, it can exist. Like here f of 1 is 2. So f of 1 can be defined, but this is still not continuous because the limit, which is -2, is not equal to f of 1, which is +2. But the key is that, f of 1 could exist. It just doesn't have to exist. And it could be continuous if that, of course, was a closed circle there. So now the limit is -2. F of 1 is -2. When the limit equals the value at the point, then we're continuous at the point. So those are all things that could have been true. But the only thing that the limiters tell me that must be true is simply what the limiters tell me, that the limit exists. So just stating that a limit exists tells me nothing about continuity, and it tells me nothing about the existence or the value of the function at the point. Please remember that. It's very important. And then we had a problem such as this. It looks like a lot of the issues based off the questions people were asking had to deal with continuity. And so there was a question that looked similar to this, and it just asked for what values of x is the function not continuous. That's all it asked. It's a very simple question. Now, the deal is when you have a rational function of polynomials, it's only going to be continuous at the values of x that make your denominator 0. That's it. Like, that's all you have to look for. The values of x that make your denominator 0. That's it. So this guy right here is not continuous when x equals -5 and 10. That is it. Problem solved. Now, they asked in the assignment, they asked a very simple question. They just asked what values of x is f not continuous. Now, they could have asked a more specific problem, and they could have asked about, well, what values of x does a function have a removable discontinuity, or an infinite discontinuity, or a jump discontinuity? And there was another question, somewhat not looking like this, but there was a question that did ask those questions. So I want to address those questions just if you happen to see questions such as that. So just in general, for a rational function, the discontinuities are the value of x that make your denominator 0. Now, if you want to talk about a removable discontinuity, then it has to be something that can cancel out. And fortunately, the way they wrote the problem, everything was already factored. So if that question was asked on here, x minus 5 can cancel. X plus 5 can cancel for my denominator. So that means -5 is the removable discontinuity. Because again, the removable discontinuity is the guy you can't cancel out. Now, in one of the virtual groups, someone didn't know that I can cancel out an x plus 5 when I have the same thing raised to a different power. And absolutely you can. So if I have x plus 5 cubed, I definitely can cancel out this x plus 5. I can do that all day long. So that's my removable. Now again, so once I take care of this x plus 5, this guy is in its most simplified form. And the only thing left on the bottom is x minus 10. So that means that x equals 10. Let me not write it under here. That means that x equals 10. Where is an appropriate place to write it? I guess here. I guess I will write it here. I didn't want to write this whole word. So that means x equals 10 is my vertical asymptote. So again, just in general, for a rational function like this, and this has been our basic functions for right now. You know, as we advance in the course, we'll get into more trigonometric functions and transcendental functions and exponential functions and logarithmic functions and things like that. But for right now, we've basically been living with these rational functions. And for a rational function, a general discontinuity is going to make my denominator 0. If I can remove it algebraically, it's removable. If I can't, it's an infinite discontinuity, better known as a vertical asymptote. Okay, and here was another type of problem we saw that dealt with discontinuities. And I believe in this particular problem, it wanted you to, well, the answer choice had different types where different numbers were either a jump, an infinite, I don't know if they said infinite or they said vertical, or removable. So that's why I wrote find and classify the discontinuities. And I think the issue on this problem for people was how to factor stuff like this. So we should be able to factor stuff like this, but stuff like this factoring, we haven't looked at a lot so far this year. And so we did factor stuff like this in pre-cal all the time. But you know, you have to get used to it again. So let me just show you how to factor something like this. So of course I need to find the values of x that make my denominator 0, but I got a factor to be able to determine if those values are removable or infinite discontinuities. You're not going to get a jump discontinuity from a rational function of polynomials. All right. So you're not going to get a jump discontinuity from a rational function of polynomials. We get our jumps primarily from piecewise functions. I asked a question, I think it was on today's bell ringer. The other main function where we get our jumps from are like those absolute value functions. And a few of you wrote that answer. That's a good answer. So I'm talking about these type of functions, absolute value of x plus 3 over x plus 3. So that function, that's going to give me a jump discontinuity at x equals -3. And so piecewise and these guys are like the main ones we see jump discontinuities, but not from a rational function of polynomials. So this is not a rational polynomials because of this absolute value. And on that bell ringer, some of you did say, a lot of you said composite functions. That's true to a certain extent. A lot of the composite functions I show you have had jumps, but you know, in theory, a composite function is really not just a function that gives you a jump discontinuity. But most of the ones I've shown you obviously have had those jumps, so we can understand the properties of finite limits of composite functions. But anyways, look at how we factor this. So the number one rule of factoring, and factoring is a big skill in your mathematics going forward. It's a very big skill that you're going to need in college level mathematics. The number one deal with factoring for any type of problem is you always check to see if there's something I can factor out of all the terms. And so if you look at the numerator here, you can factor out x squared. So you can take out an x squared, and that'll leave you with x squared minus 9. And if you look at the bottom, you can factor out an x. So you can factor out an x, that'll leave you with x plus 3. Now, you also see here, you should notice this is a difference of squares. Now, in an actual problem on AP Classroom, it had difference of squares, but it really was no need to factor it because nothing would cancel out. Well, on the problem I made, there is a need to factor this because, I mean, look, you have this x plus 3 down there. So you do want to factor this difference of squares. And hopefully you understand when you have difference of squares, it's, you know, you take the square root of this term, it's x plus that, x minus that. So this is going to be x plus 3, x minus 3. and it's over x times x plus 3. And if you have further issues on factoring basic stuff like these difference of squares, communicate that with me or come to the virtual hours. We'll go over it because it's definitely stuff you need to know how to do. So now that I have factored, I can see what I can cancel out. Whatever I can remove, that's going to represent my removable discontinuity. What's ever left in my denominator, if anything, is going to represent the vertical asymptote. So in this particular problem, I can cancel out this x. And so when you cancel out x or a multiple of x, if you can cancel out x or x squared or x cubed or 5x or 7x or 8x, any multiple of x, the value is 0. The value that makes a multiple of x 0 is 0. So x equals 0 is removable. It was removed. And it also so happens that this guy can be removed as well. So -3 is also a value of x that represents a removable discontinuity. And for this particular example, now it's in its most simplified form and nothing is left in my denominator. So this one doesn't have a vertical asymptote or an infinite discontinuity. So this example only had removable discontinuities. All right, so I'm sure you remember the problem that was similar to this guy. And so what they did is they gave you a piecewise function with 5 pieces. Again, I said, most of the piecewise functions we're going to encounter are going to consist of 2 pieces, but you will at times see piecewise function consisting of more pieces. You probably won't see one consisting of more than 5 pieces. So this is probably the biggest piecewise function you'll see. And so what we're doing is we're checking the continuity at these different values. I think what the problem wanted to see, I think the problem, it said, f is continuous at each of these numbers and which of the following statements is false. So to understand what is going on, I'm just going to check continuity at each of these points. And so I hope you understand. And in my opinion, this problem was the hardest problem on that assignment. So I really want to make sure you understand this particular problem. Now, so let's just go through it and let's check the continuity of each value. So when I check the continuity of a piecewise function, what needs to happen is every piece affiliated with that value must be equal when I plug that value in for x. So you guys are very familiar, and from what you're telling me, you're very good at those problems where it says find the value of k to make the function continuous at a certain value of a piecewise function. And what do? We plug in the number for x and we set each piece equal to each other and we solve for k. Well, that's what we want to see here. We want to see each piece that's affiliated with the particular number. We want them to be equal to each other when we plug the number in for x. So let me check 2. Now there's 3 pieces that are affiliated with 2. This guy, which is to the left of 2, this guy, which is right at 2, and this guy, which is to the right of 2. So I need all 3 of these pieces to be equal when I plug in 2 for x, if this guy is going to be continuous at 2. So let's see what happens. So if I plug in 2 for x here, that's 6 plus 5, that's 11. Okay, when x equals 2, it's already 11. When I plug 2 into this piece, that's 2 cubed, that's 8, plus 2, that's 10, plus 1 is 11. So for 2, I got 11 for all 3 pieces that are affiliated with 2. So 2 is definitely continuous. That guy's good. Now check 4. Now 4, the piece that is affiliated with 4 is only one piece. This is it. 4 only fits into this guy. So it's not multiple pieces that 4 fits into. 4 only fits into this one piece. This one piece is a well-behaved polynomial function. Polynomial functions are continuous if we're just looking at one polynomial function. So since 4 is only inside of this one polynomial function, it's definitely continuous. There's nothing to check. Again, I don't have to look at multiple pieces for 4. I mean, just look at the provisions on each piece. 4 only fits into this guy. And so this guy is going to be continuous. Okay, what about 5? So 5 is like 2. It has 3 pieces. Here to the left of 5, here equal to 5, and here greater than 5. So I have to check all 5 pieces. So I'll plug in 5 here. So 5 cubed is 125, plus 5 is 130, plus 1 is 131. Perfect. And at x equals 5, it's also 131. Perfect. But when I plug in 5 into this guy to the right of 5, 5 times 30 is 150, plus 1 is 151. So I didn't get the same number for all the pieces that go with 5. So the function is not continuous at x equals 5. Not continuous at x equals 5. And what about x equals 7? The case of x equals 7 is similar to the case of x equals 4. Remember, for x equals 4, it was only affiliated with this one piece. Well, x equals 7 is only affiliated with this one piece because x equals 7 only goes with the numbers greater than 5. And again, this is a polynomial function. It's a linear function. And so it's well behaved. So it's going to be continuous. And so x equals 7 is definitely continuous. All right, all these problems dealing with continuity, very interesting. And here's the last example that I'm going to do that kind of mirrors stuff you saw in that AP classroom assignment. And yes, you guessed it, it's another continuity problem. And the problem I'm trying to model here is a one problem where they had you look at a student's work and determine where his mistake was made. And so I'll go through this problem and kind of do it the way it was done there and show you the mistake that was made in the problem. Quite honestly, if this was really the question, if this problem was really just asking me to check continuity at 4, I wouldn't go through that process. I would just plug in 4 for x and see what I got if that really was the question. But I want to address the question in the way it was posed for that particular problem. So the first thing they did is they found the limit of f of x as x goes to 4. And so they took the limit of this guy as x went to 4. And they factored. So this one would be x plus 7 times x minus 4. And on the bottom would be x minus 2 times x minus 4. So you can see that the x minus 4s would cancel. And then you can just take the limit as x goes to 4 of x plus 7 over x minus 2. And from there, you can plug in 4 for x, and you'll get 11 over 2. And I think that was like steps 1 and 2. And that's fine. That's definitely the limit. The limit as x goes to 4 of this function is definitely 11 over 2. And so what they were trying to do to check continuity, of course, they were trying to check if the limit as x goes to 4 of f of x is equal to f of 4. So that's what they're trying to check. So they first started off in finding the limit. And then they went to find f of 4. And to find f of 4, they plugged 4 into this function right here, this function. They plugged 4 into this guy right here. And of course, they got the same thing, 11 over 2. But that's wrong. So that was step 3. That's wrong because this function isn't f of x. This function is f of x. This guy has been simplified. So this is not the exact same as f of x. You know, it's real close to f of x, but it has a removable discontinuity at 4, the difference between f of x and this guy. This guy doesn't have a removable discontinuity at 4. So this is not the function f of x. What you have to do for this problem to find f of 4 is you need to plug f of 4 into the original function. Now, it's easier to plug it into the factor form. It's a lot easier to see what the answer is going to be plugging in here versus plugging into all this stuff. But you can clearly see here, if I plug in 4 for x, I'm going to get 0 over 0. So f of 4 is undefined. And since f of 4 was undefined, of course, the function is not continuous at x equals 4. Because again, to be continuous at a point, the limit must exist, the value of the function at the point must exist, and they have to be equal. Okay, so I hope that little review kind of helped clear some things out that caused some problems on that AP classroom exam, and I hope this information helps you to become more prepared for your test.